So the next talk in this session after the break is by Evelyn Tang from Rice University. She already has a title, Predicting Robust Emergent Function in Living Active System or Stochastic Systems, as you want. It's really nice that you're able to come, you're able to give this talk. Would have been better if it was in person, but as I told the other speaker, that if you could keep it to 30 minutes talk and then 15 minutes for questions, that'd be great. Give or take a few minutes. And I can give you a 5-minute reminder before your 30-minute is up. And you can take it from there. Does that sound good?
Actually, I was thinking of also pausing in between the talk just to start discussions already. So I'll try to.
Yeah, maybe that suits you. So without much more, please, Evelyn Tang.
Thank you. I'm thrilled to be able to speak to all of you today because I think complex adaptive matter is so fascinating. For instance, your brain network looks and lights up in such a different way from mine, and yet we can communicate and maintain many similar biological functions. Or going down to the small scale of cells, there's often a lot of stochasticity or small copy numbers. And yet, despite all of this heterogeneity or stochasticity, complex systems or living systems show robust functions. For example, persistent timescales in circadian rhythms or memory. And how to obtain this robust function remains unclear theoretically for many complex systems. And so I think this is a fascinating topic to discuss with all of you today. And there are, of course, many theoretical challenges why this is something that's difficult to describe. For example, statistical mechanics usually assumes identical particles in equilibrium, isolated from the environment, etc. So thinking about some examples of adaptation or self-organization that's particularly interesting, some here are that of a biological oscillator, or the stochastic growth or shrinkage of microtubules, and these are cytoskeletal filaments inside a cell that's important for the growth and mobility of cells, as well as the synchronization of multiple oscillators. And these are all emergent dynamics. In other words, the system consists of many parts that act together to produce more than the sum of each part. And of course, as theorists, we would like to be able to analytically predict this global dynamical or functional state of the system. And so today, I would like to introduce a framework where even though these phenomena appear unrelated, what I want to show is that similar dynamics can all hinge on the edge state of a topological phase. And topological phases are familiar to many of you. And here, so I'm going to illustrate some of why I find them so fascinating, and in particular that they can support robust dynamics. So in this canonical example, which is the quantum Hall state, which is a 2-dimensional electron gas system. And so here in this system, there's a perpendicular magnetic field applied, such that which makes the electrons form these closed cyclotron orbits. And so in the bulk of the system, the electrons are pinned and so they don't go anywhere. They just make these orbits. But on the edges of the system, they skip around to form these chiral edge currents, this one in one direction, in this direction, and this other currents in this other direction in the semi-classical picture. And what is interesting here is that now, even if you block some part of the edge of the impurities, then this does not destroy this edge state, because then there will be a new edge in the system. And so let's imagine that here we just block part of the system and the electrons will just go around the new edge. And so in this sense, the edge states are robust to impurities or deformations. And this is a nice property of topology, and one reason why it's been so popular in quantum systems. And more recently, there's also been proposals to realize these in classical systems. And this also includes in stochastic systems, for example, in this work from the Chicago group, in which they proposed a model for a one-dimensional system, where here again, you see these notions of this bulk state and an edge state, where now here, because of this some kind of chirality in these systems, there is again a buildup of probability density at this interface between these two bulks. However, of course, in these one-dimensional systems, the edge state is necessarily zero-dimensional. And so this edge state here doesn't move, it forms polarization. And with Jaime, my collaborator at the Max Planck, we were wondering whether we could obtain propagating edge states like in the quantum Hall effect in these stochastic systems, which are desirable also for its robust properties. And so you might be thinking that this is strange. Why would I try to describe biological systems or any systems that exist in real space with a description that is two-dimensional. And that is true that biological systems are three-dimensional in real life. However, what we thought about instead was to think in chemical reaction space. And there are many examples of out-of-equilibrium cycles in chemical reaction space that's fueled by the consumption of ATP or GTP. This is exactly what Oleg was saying in his previous talk about how chemical energy essentially is converted to a kind of mechanical energy. One example of this would be futile cycles. And this is essentially a very simple motif. This is just a phosphorylation and dephosphorylation reaction. But this is propelled by consumption of ATP, such that even though this is an energetically costly reaction, so that because it moves and it moves right back to where it came from, this is something that does cost energy. And yet at the same time, we see these motifs in many different biological systems. And so this is very interesting, and hence the name futile cycles, because they seem to go right back to where they began and they don't do anything, and yet they show up in many different places. And so we hypothesized that these futile cycles could play a role similar to electron orbits in the Halefect, because they, just like electrons in the bulk of the system, they move around and don't seem to do anything, but yet their presence supports edge states on the edges of the system, which in this case is the edges of this chemical configuration space. So let me show you a model. And after discussing the models, then we can look at when the system is topological, as well as what dynamics we can obtain. So let me give you a simple model, stochastic model, which is a polymer system. And in this example, there's two types of monomers. Here, there is a purple monomer and a green monomer. And the numbers of each monomer are given in these brackets. So the first number is the number of the purple monomers. The second one is the number of the green monomers. And there can be transitions as the monomers as these polymers grow and shrink. So here we can see that the system grows a green monomer, grows a purple monomer, so on and so forth. And when the system is in a particular configuration, because it can grow or shrink in any way, we also provide an additional tag, this tag ABCD, which tells the system what's going to happen next. So this is an internal transition so a tag A will then tell the system to add a green monomer, tag B tells the system to add a purple monomer, and so on and so forth. And so then this allows it so that for each state of the system, it actually has three indices, these two numbers, X and Y, as well as this internal state that indicates what transition is going to happen next. And then for each particular configuration, we can also allow, for each configuration now that there's 4 internal states, we can then also allow for transitions between them. So as indicated by these gray arrows. Now what happens is that this can then, at the 4 internal states for each configuration, this can simply form a unit cell here that we can then use to tile a lattice space. And so this, for example, unit cell like in this blue box, so where in this lattice, this x-axis is the growth of the purple monomer and this y-axis is the growth of the green monomer. And so that this cycle that I showed you up here would form exactly this box with these solid arrows up here. And then this cycle with these, that's just amongst these internal transitions of the same kind of configuration, then forms this gray box that I'm showing down here. And so it's just a way of writing all of these arrows in a lattice form. But writing it as a lattice actually allows us to see something new, which is now that when we look at the system, we see that actually when these black rates are larger than these gray rates, the system is topological. And what that means is that in that case, when the system hits the edge, it will stay on the edge. And so we can just see this just by looking. So let's say the system hits the edge and it reaches here, we can only move forward. And since these black rates are faster than the gray rates, we'll be likely to move forward. Here it can only move forward, or be likely to move forward. It can only move forward, it has to round a corner, and it will just keep going up and around. And now, even with missing components or obstructions, let's say this particular state is inaccessible, or for some reason now the system is blocked and it can't access these states, it will just still go around the corner and it will keep going such that this edge dynamics will still continue. And this was really exciting for me to see because for a long time, we thought that topological states could only exist in very regular or clean systems like crystalline lattices or semiconductor systems, and certainly not in soft or squishy systems like in biology that's so irregular. And instead here, what we showed is that by going instead to configuration space, we can get this regularity by thinking about the assembly and disassembly of components that happens all the time in these stochastic molecular systems that allows us to use these tools in the space of molecular configurations, in other words, in these everyday systems. And another feature of our model is that because you're essentially taking the same motifs and then using them and repeating them again and again, it's the same parameters that are just repeated many times. So in this case, for example, we have just two parameters repeated over and over, this black rates and the gray rates. And then this allows us to then interface nicely with experimental systems, because here we have very few parameters of the system. Or we can make predictions by just specifying two, for example, in this case, two parameters of the system. So in this case, we can predict that the topological phase occurs when these black rates are faster than these gray rates. So let me stop here and just see if there is any questions, because then I'll be using this very same model to show you how this model could describe something that's closer to phenomena seen in nature. And there are many directed cycles in biochemical and other processes, but let me just stop here first to see if there's any questions. Okay, great. Seems like everyone's on board. Fantastic. So here we can see that these systems can support this global cycle that goes around the entire perimeter of this system, this global periodic cycle. And so they can easily form an oscillator or a kind of clock, since it moves around this space. And there's many different oscillators in biological systems. And here I'll show an example of how this could work in the KalABC system, which regulates the circadian rhythm of cyanobacteria. And in this system, the monomers, so these are the monomers of the system, can do many things. For example, they are known to have certain 4-state directed cycles of phosphorylation. Here, moving in these, this directed cycle. And these monomers can also assemble into hexamers. It can also have active and inactive conformations. And so clearly there's many things that can happen in these systems. So even though we have isolated these systems, we can reproduce its dynamics, but because there's such a large phase space of many different transitions or phosphorylation or conformational changes that can happen, we don't actually know which ones are crucial for the dynamics to happen. So this is what has been observed. And let me show you a model of what we propose. And so here again, we're using this 4-state directed cycle, this motif that we saw earlier, which is plausible given what we know happens. And in here we have two kinds of transitions. This is a conformational change that we denote going from this diamonds to the circle. And this is a phosphorylation that we show by the addition of this yellow circle. And so we allow cycles that have conformational changes and phosphorylation respectively. And as before, we have, for the same configuration, transitions between the internal states of the different internal states of the same configuration. And this is exactly the same as the model that I showed you earlier, just that now here this x-axis is changing in conformational change, and this y-axis is changing in phosphorylation. Just that now this is a bigger lattice then one should imagine that this lattice actually goes to from 0, 0, instead of just going to 3, 2, it goes to 7, 7, because of the number of states that can exist in this hexamer. And so what would this give us in the topological phase? In the topological phase, the system would simply undergo these large cycles of all of the hexamer undergoing conformational change, all of them undergoing phosphorylation, all of them undergoing conformational change, and all of them undergoing dephosphorylation. And this is actually the same dynamics as what has been proposed in this established model in literature, just that for them, they have to assume that many of these intermediate transitions do not exist or are negligible somehow, that these arrows are much weaker than these arrows at the end, because they propose that the hexamers do undergo all phosphorylation, all conformational change, all dephosphorylation, all conformational change again. But here they have to make several assumptions to impose this edge what we see as edge dynamics by hand. And they also break this invariance between C0 and C1 that we don't have to in our system. And so this is dynamics that can emerge, reproducing this established model with simpler assumptions in here. And I want to discuss a little bit about how to calculate the topology in these systems, or in particular, how to see the winding number in these networks. And essentially here, these systems are governed by the master equation, where W describes the transitions between the different states of the system. And essentially, because all the states of the system can be laid out in a lattice and the transitions between them are then encoded in here, we can then calculate the barrier connection of the system by examining W. And this is because there is a connection between a particle that's moving in a lattice and its barrier connection, which was first formulated by Zapp for electrons in crystals. And where for electronic systems, here in the Brillouin zone, the electronic wave function can wind around the Brillouin zone. In our system, our lattice coordinates are in real space. In the electronic systems, lattice coordinates are in real space. In our systems, they're in configuration space, but this still allows us to then write the system in reciprocal space and then look at how the system states winds in this space. So more specifically, what we do here is to use the fact that the barrier connection is typically calculated from the Hamiltonian, which obeys the Schrödinger equation. And using the eigenvectors of the Hamiltonian, then this quantity Q can be calculated. And then integrating Q over reciprocal space can then yields either 0 or pi. And so if it yields 0, the system is trivial and does not particularly favor the edge. And when the system is pi, then when the integral is pi, the system is topological and the dynamics will be dominated by the edge states. And what we use essentially as a mapping by observing that the Schrödinger equation is essentially identical to the master equation up to an I. And hence, if we map our master equation to a corresponding Schrödinger equation, then what we get actually is that this corresponding Hamiltonian will have identical eigenvectors. It will have a different eigenvalues because of this I, but the eigenvectors will be the same. And because the barrier connection is calculated only from the eigenvectors, we can then calculate the barrier connection of our transition matrix. Another way in which we could look at the topology is also to use, just to simulate the system, this is stochastic system, so that we can use the Gillespie algorithm to simulate the master equation. And what we see is that, for example, in this regime, the system starts to go around the edge. So this is the two-dimensional space. Here, time is the vertical axis. You can see that initially the system makes a random walk in the bulk of the system. Once it hits the edge, then it starts to stay on the edge and keeps going around. We can also directly solve the master equation. No, sorry, I think this is, yeah. And this is just the steady state density so that at long times we see that the system does stay on the edge. We could also directly solve the master equation to see how the lowest, the zeroth eigenvector is distributed. And what we see here is that this edge state is on the edges and is in fact exponentially localized at the edge. And this makes it so that, and this exponential localization is very useful. It makes it so that these edge states are robust, even in small systems where you just have a number of unit cells. So for example, in here, the edge physics would still remain robust. And this is very useful because what I told you about going to reciprocal space, etc., may make one think that these results would only work in very large systems on periodic systems. But in fact, here we can see that because in this particular conditions, for example, because the edge states are localized, so that this would be robust even for smaller systems or even parts of systems. So that if I have a network in which part of the subsystem is topological and has a winding number, then, and if the other part of the network is trivial, then there will be an edge state in between these two subsystems. And so then these tools can be relevant to real life systems that might be messy or less regular than what I've shown you so far. So I'm just going to pause again in case there's any questions. And I really just have a last couple of examples of different dynamics before I wrap up.
I have a question. I mean, how did you do the Fourier analysis of the configuration space?
So because so these systems, if because this can be laid out as a periodic lattice, essentially, so it's periodic, then we can then just write down its Fourier description and look at its topology, and using the bulk boundary correspondence, which is that when the periodic system has a topological invariance, then when the system is open or has finite edges, then there will be.
You assume the system has no boundary?
Can you say that again?
In order to do the K-space analysis, you assume that the system has no boundary?
Yes, so we do the K-space analysis in the periodic system where there's no boundary, but the results of the analysis in the periodic system then tells us that when the system has a boundary, then the dynamics will stay on the edge, or that there will be this edge state. So the analysis without a boundary tells us about what happens when the system does have a boundary.
Evelyn, this is Andrei here. Is there a parameter that has some biological significance that can put you either in topologically trivial or non-trivial class? Like in SSH chain, this would be a ratio between the two kinds of hoppings. Is there something equivalent in your networks that could determine whether the system has the Berry phase pi or zero?
Yeah, that's a great question, and it would be great to work with experimentalists more on this. So, for example, in the next section, I'm going to show how this could model growing and shrinking of certain cytoskeletal filaments. And in there, experimentalists do have ways of, enhancing the growth or also poisoning these microtubules such that they grow less. And so in some ways, changing how well these systems grow or shrink. And that would be changing the equivalent of these kinds of hoppings. And so that could be something that would be very interesting to see whether or not we could see the different phases. There's probably also many complicated things that happen in these systems, but that would be one thing to try. So let me just show a couple of examples quickly, and then we can have, and then we can discuss. And so this is now the example that I was just mentioning to Andre, that in here, so I had just shown you something in a square lattice. We also have a different example of now a 3-state system instead of the 4-state system we had before, in which here the two indices now, one can still represent growth. So the number of these little units is the first number. The second number is their conversion. So shown by this little square. So this could be, for example, conversion from a GTP to a GDP bound monomer. And so here, this is conversion, adding an unconverted monomer and removing this converted monomer. And just as we did before, we have an internal state that tells the system what's going to happen next, as well as transitions between the same internal states of, between the internal states of the same configuration. And this can actually be laid out as a KalABC lattice, where similarly, where this axis is growth and this is conversion and this is removing of the converted monomer. Where similarly as in the topological, phase here, we have protection of the edge state, which you can check numerically, for example, by seeing that this does go around after a while and the system does stay on the edges of the system. The dynamics do stay on the edges of the system. So this system now, we can also change it a little bit because essentially we have these repeated motifs and each motif has three gray rates and 3 black rates. And so if we change one of them, let's say we change the upper right rates in here, then we can also see dynamics that are more interesting than just staying on the edge. And so here, if we make this rate slightly faster so that it's faster than the other gray rates, but not as fast as these black rates, what's going to happen is that the system will still favor the edge. But what happens now is that the system will grow slowly, convert quickly, and then it's going to shrink again here slowly. And this forms dynamics like so. So it grows, if we just plot growth and shrinking here, it grows here, it converts quickly and it shrinks and grows and shrinks. But what also happens is that sometimes we see that in this particular edge, it doesn't always make it to the edge all the time. Sometimes it cuts out, and that's what's happening at these things. So it makes these smaller triangles. And what was interesting is that these dynamics are looking very similar to the dynamic instability of microtubules, which are these cytoskeletal filaments that I mentioned, that in a cell, these filaments don't grow and shrink in any kind of predictable manner. In fact, they seem to grow and then they abruptly shrink all the time, and they grow to different lengths before shrinking. And this is something that's very difficult to understand why theoretically. And here with 3 rates, we can obtain a pattern that looks similar to what has been observed experimentally. I'm just going to mention one last thing that we can do, which is then we can couple systems, because here in chemical reaction space, it is natural to think of these boundaries as also being prescribed by the number of available monomers that we have in the solution. So here we have two systems, one that starts growing from the left towards the center, one that starts growing from the right towards the center. If they share the same pool of, they're both drawing from the monomers in solution, once they exhaust all the monomers in the solution, they will hit each other, and then they will have to go on to the next reaction. So they'll have to go up in space. And so that's what's happening here. And one thing that we can already observe is that when they move up at this shared boundary, that this shared boundary changes in location every time in this stochastic system, which is already nice because in solid state systems, we don't have dynamic boundaries that change with time. But also because of this competition that they have of going up each time, of wanting to compete for the monomers in solution, that after a while they do form anti-synchronization. So this is basically the end of my talk. Should I just stop here? I was going to mention some open directions, or is it better to leave time for discussion? I think I'm probably already a little bit over.
No, please do. You have time. So you have not even exhausted the 30 minutes. So you can definitely
Oh, I
say
started
more.
at 5:15. Oh, okay, perfect.
Yes.
So yes, I'll just mention a couple of just broader considerations, which is that more generally, these out-of-equilibrium systems do require new theoretical tools. And here we use this master equation. And the transitions that we had about these systems that convert chemical energy into mechanical energy or something else, they break detail balance and have non-zero currents, which is necessarily described by a non-symmetric transition matrix. And mathematically, this is very interesting because topology has been mostly developed for energy conserving closed equilibrium systems, in other words, for Hermitian Hamiltonians. And instead in biology, the opposite is typically the norm, in which we have non-reciprocal interactions. And for example, in this predator-prey interaction. And these non-symmetric transitions actually, or these non-symmetric transition matrices, and falls instead under a whole different framework of non-Hermitian physics, which has beautiful properties and has been of recent interest. So some of its very pretty mathematical properties are that now, of course, these matrices have complex eigenvalues, and these complex eigenvalues can also now show interesting structure in the complex plane. For example, in this work from Liang Tu's group, they show that there is a kind of, that the eigenvalues can show some winding in the complex plane. These systems can show these exceptional points, which are singularities, that in which the eigenvectors can coalesce into just one eigenvector. And this is distinct from Hermitian systems, in which in Hermitian systems, when we have a level crossing, the system actually still has two distinct eigenvectors. And in this case, there is only one. And now there is these interesting square root branch points. And this gives rise to new properties. For example, in here, this topological invariance now can be described just by the eigenvalues, which doesn't exist in Hermitian systems, because in Hermitian systems, the eigenvalues would be real. And so the winding would come really visible only from the eigenvectors. So let me just go over what I've told you so far, which is that by using simple repeated motifs here, we propose a topological framework that predicts the emergence of these robust global dynamics. It provides a universal mechanism for different phenomena from global clocks, the stochastic growth and shrinkage and synchronization. And this framework can be broadly applicable to different biological and chemical systems, especially these non-equilibrium, with these non-equilibrium transitions that allows analysis in many different scenarios. Overall, I'm just going to mention some other topics I enjoy thinking about. So today I've told you about topological cycles and phases. I also, my group also studies information, learning, and control in the brain. And I think that's also one reason why I'm so excited to speak at this interdisciplinary conference with all of these different topics that are being discussed, and to discuss all these further with you. I want to thank my group at Rice, especially my student Changbin now, who is investigating especially these microtubule dynamics. Jaime has been my collaborator at the Max Planck, and it's been really fun to work with him. And my new group is also hiring students and postdocs, so please spread the word to anyone who's interested. I'm happy to discuss any more. In the meantime, I'm going to leave up this video of this etch date in configuration space in case it's helpful to see exactly what happens in the topological phase and in the trivial phase.
Thanks, Evelyn. That's a great talk. So if anybody has any questions, please raise your hand using the reaction button. There's a raise hand feature there. If you cannot locate it, please just ask your question by chat. So Daniel, you had a question. Good to see you, Daniel.
Good to see you. So Evelyn, beautiful talk. I guess maybe two quick questions. One, of course, microtubules also collapse and disappear. Would that be an allowed feature here?
Well, let's see, let's go through that slide. So, yeah, so you're talking about how they sort of collapse suddenly.
Yeah, I mean, it actually can even just go, right? I mean, but that's, okay. So you're saying that all the way down to the collapse.
Yeah, I think, well, there's a couple of things. One is that it might be a matter of time scale, because here that, ours sort of collapse one at a time, microtubules collapse all at once.
Okay.
And it would be interesting to understand better whether in the real systems, it's just a matter of, they just collapse so quickly. Does any structure in the collapse at all, or we just don't see it? Yeah, I think it's a great question to understand whether or not we can match this more closely to the actual microscope.
Okay. I guess this just the other question, which is maybe you already sort of alluded to it, but there are, of course, oscillations in the brain, famously that Hopfield and collaborators pointed out for the olfactory system, Lee and Hopfield pointed out for the olfactory system, for example. And so I guess, have you thought about applying this to oscillatory modes in the brain? And I'll just stop there.
Yeah, the brain is extremely interesting. So I have thought about it. These models are still pretty simple. And of course, in the brain, neurons have somewhat more complicated dynamics, but it would be interesting to think about what is a good description of that. Because it is true that there are sort of also, yeah, as you pointed out, sort of large scale dynamics in the brain, and it's difficult to actually model those or get that. So that would be something very interesting to explore.
I think Jim had a question.
Yeah, I was wondering if there could be some role, some interaction effects between these kinds of things that you're talking about and entropic considerations, maybe systems that have ways to avoid entropy increase, as some living systems certainly do. So just generally whether entropy could have a role in these kinds of considerations.
Yeah, I mean, that to me connects to one feature that I think is very useful here, which is that of this robustness, because systems do want to, whether they're trying to grow in a particular pattern, if something happens, let's say a particular cell gets knocked out, or if they're not being able to, obtain the nutrients that they need at that time, they don't want to set back the entire developmental or functioning program. And so to have a kind of pattern that I think they don't have to radically rewire, but the dynamics can continue without, even as it faces different changes in its conditions, and that these topological models can support dynamics that will persist even with changing conditions. I think that's something that can be helpful for the program of the organism. It's a little bit different from entropy. I think entropy considerations, yeah, I would love to understand more what you mean by that, because that's a very broad term and there's many different ways in which we can consider entropy, I think, from energetic considerations to, what can we quantify more, whether this robustness can be a resource. I think there's different ways to approach this, but I'd love to hear what you think about how better to break down what we mean by entropy considerations.
Piers?
Yeah, thank you for a great talk. Your model went past very fast, and what I wasn't clear about was what sets the edges in configuration space.
That's a great point. So in here, this would be, well, it depends on the system. So in the system in which we have those, in which they were those hexamers, then just the number of the fact that a hexamer has 6 monomers and each of them can change in conformation at a time, and or each of them can then can be phosphorylated or dephosphorylated at a time. The fact that there's 6 monomers in a hexamer, that creates the edges of that configuration space. So it goes from 0, 0 to 6 by 6, and that forms a lattice. And then in other cases, if the monomer is growing or shrinking, and if that is the particular configuration space that we're talking about, then that could be limited by the number of monomers that are available in solution to be added to that monomer, for example. But definitely I think it depends on the system, and this also points to something that we're exploring right now, which is that we in many systems we may not expect just hard boundaries, because we could expect a system in which it becomes less and less likely for the system to keep growing past a certain length, and so that would be a case in which there's more like softer boundaries. So instead of growing radically and coming up, there's some kind of softer boundary where it goes into the next phase. So that would be very plausible, given what we know in most chemical systems. So that's definitely, the nature of the boundaries is definitely something that would depend on what we're studying, and to adapt our models also to those conditions. And
just to follow up on that, of course, in the electronic analogs, the edge states are not necessarily very tight to the edge, but can spread far into the bulk as you approach the topological phase transition. Is there any analogous notion here? And what is the topological phase transition for your systems?
So a few things, yes. So what I've shown you is that I showed you sort of the let's just go back to this model. So I've shown you the most basic model in which there's only one transition from all our transitions are unidirectional, and this is obviously the most extreme chirality. In many cases, or I suppose the Hermitian limit would be when hopping forwards and backwards is actually equal. And once we start approaching that limit, then these edge states can start to move away from being exponentially localized at the edge to start to decaying into the bulk. So there's 2 ways, I suppose, in which the edge states could start to bleed into the bulk. One is by moving towards the Hermitian limit, and the other one is by moving towards the topological transition. And depending on the system itself, that is a way in which we could start to see this larger length scale. And what would set a topological transition? I think that's a very similar question to what Andre asked. That would be that these rates then would change, so that we know that we're in a topological phase when these black rates are much faster than these gray rates. So this assumes a very, very particular separation of timescales. And once those timescales aren't so well separated, or once the gray starts to become larger than the black, then that's when we would go into the trivial phase. So changing these chemical rates, how likely it is for something to bind to something else, that is something that normally experimentally we would change by changing the chemistry in the system, or if the system itself tends to change the rates because of some, let's say, external conditions.
And would there be an analogy between a gapped system and a gapless system, like in topological systems?
That's a great
of course, there's a question of how far you can push the analogies, but obviously a topological phase transition in a metal insulated transition is a gapless system, and it's one point which is gapless, and you go away from that, you go into a metal, and you see vile semi-metals and things like that. Is there any possible analog here?
So these systems, what they map to most directly would be something like the ZAP phase, which is in symmetry protected phase. So there probably are other constructions that could map to different kinds of phases as well. That would be really fun to explore, but yeah, this one has.
Thank you. Really fascinating. Thank you.
Any other question? Nobody has questions. I had a question. It's a very, because I just don't know enough about this non-Hermitian. Towards the end, that was very interesting for non-equilibrium systems and non-Hermitian Hamiltonians. I was curious about to learn more about this, how you get the Berry phase or any information about the topological nature from the eigenvalues rather than eigenvectors. And is it only the real part that's relevant?
No. So let's look at this. Try to find this slide. So actually, what happens here is that yeah. So this comes out of this paper with, I think, Shen and Fu, etc. So you can't only use the real part, because what happens is that if you only want to look at the eigenvalues, and so this is actually the complex plane, and then this is the Brillouin zone, and so what you can see is that essentially the eigenvalues can wrap around in a non-trivial way in the complex plane, and so if you only had the real part, you wouldn't be able to see this, or it would just project to a line. And so
I see now. Actually, there was a color code, so actually it wraps around only together with the imaginary part. Yeah. Okay. Yeah, I see that. Yes, okay, so that's very interesting. And do you actually get something like a Berry phase, or what do you call it? I mean, out of this, or?
So they called it vorticity in that paper. So yeah, it is something that I don't think it's distinct from the Berry phase. I mean, the Berry phase exists in Hermitian systems. One could define the Berry phase in non-Hermitian systems as well, but that is something that's still defined using the eigenvectors. To define something just from the eigenvalues in here, this is something that's different.
Very interesting. Now, Piers, did you have another question?
No, I sorry, I forgot to take my hand down.
Okay, so anybody else have any questions? I don't see any more hands, but if you have, please ask. Otherwise, that was a very fascinating talk. Thanks very much, Evelyn. Thank you again.